Welcome to the first Presto Summit in India.
Hi everyone, my name is Ankit. I work in and around Presto at Qbol, and I'll just be setting up by explaining Rubik's briefly, and then Garvit would explain the changes we have done in open source Presto to better make use of Rubik's. Okay, so first of all, Rubik's, what is Rubik's? So Rubik's is a data caching layer which can be used with any engine that uses Hadoop file system to access data. And so, first of all, why do we need Rubik's? Because as all of the presenters before us presented, most of the data today is present in cloud storages. And once you go to the cloud storage, there are certain advantages and also disadvantages. So this is mostly covered in previous talks, but I'll just go through quickly. So first of all, while using cloud stores like S3 or BlobFS, you get near infinite capacity. You don't have to manage it yourself. There's ease of usage, and yeah, also it's inexpensive. But there are also certain disadvantages that or trade-off that you have to pay, which are that since the data resides farther now, so there are higher network latencies and backoffs or throttling that are done by most of these cloud storage providers to make sure that everybody gets the data. So, and also one more point which is not mentioned here is the unpredictability. That is, 1 GB of data can sometimes be fetched in a millisecond, or sometimes it might even take seconds. So yeah, those are the things that you get with using a cloud storage, and that's why we needed a caching framework so that whenever the data is accessed multiple times, we can cache it locally on any of the flash drives or hard drives, and basically repeated usages can pick up data from there. So for that, we developed Rubik's in-house in Qbol first, and then it was open source. So this is currently open source. There's a link in the talk at the end. So yeah, what were the goals and basically the objectives that we achieved via Rubik's? First one was that it has to be extensible to multiple engines, because in Qbol we support Hive, Spark, Presto, mainly as the open source engines. So the Rubik's cache that we developed had to work with all of these. The second one is, since most of the data is stored in columnar format, so the data that we cached has to be in a certain format so that columnar formats are benefited. And third, and one of the important ones which we didn't find in the existing caching frameworks, was that they did not have support for autoscaling. So when the cluster autoscaled or downscaled, you have to separately manage the cache. So we wanted to make it work with autoscaling. And the fourth one was that we wanted it to be shareable across the engines and instances. So that's why it is a separate daemon, lightweight daemon which runs. So even if there are multiple engines running across the same set of nodes, they can share the cache. So yeah, with these objectives, we implemented the cache. And so I'll briefly talk about the architecture, the three main components, and yeah, if there are any questions regarding details, we can cover it later after the talk. So the first one is the split ownership assignment system, which basically calculates and keeps a map of which split has to be cached or is cached on which system. The second one is data caching system, which is responsible to cache the data if it is not there when the engine asks for it, and return it to the engine. And the third component is plugins. For each engine that we want to work with Rubik's, we have to they have to just implement one of the plugin. So yeah, the only caveat is the engine has to use Hadoop file system to access, at least that interface to access data. Okay, so let's look at a bit into detail into what are the components and what are their responsibilities. So for the first one, the split ownership assignment system. So whenever, let's say, consider Presto. So when Presto asks from the file system to get a list of locations, the block locations of data, then the Rubik's file system, which we have implemented, basically now, instead of initializing Presto with S3, we initialize it with S3 Rubik's file system, and tell Rubik's that the underlying file system, Hadoop file system, is S3. So yeah, the Rubik file system calls the engine to get the list of nodes which are currently active. It logically splits the file into, here also what we call it, split. So let's say 128 MB splits. And then using consistent hashing, it assigns those splits to different nodes. So we use consistent hashing so that when the cluster upscales or downscales, we do not have to drastically redistribute the data. So yeah, that's the main part of this component. The second one is the data caching system. So yeah, is there any question? Okay. Yeah, so the second part is the data caching system. This part is responsible for fetching the data, managing and bookkeeping which data has to be cached on which system, and if it is cached, the exact location of that. So yeah, so if we look into the diagram here or the chart here, basically what happens is whenever the splits are assigned to the worker nodes, after that, when the worker node asks for data, so there's another component called bookkeeper here. There are many more components. We'll just assume those all subcomponents are part of that. It first checks whether the data is available locally or not. If it is available locally, it returns that. If it is not available locally, it checks if any other of the nodes on the cluster have the data. If yes, then it fetches the data from those nodes and returns. And if not, then it calls the remote file system and basically gets data from there, caches it, and returns it to the engine. Now, one important detail here is that the data that we cache, it's in 1 MB blocks, just for the sake of efficiency. And since the data format that we're using is columnar, then 1 MB mostly works. So yeah, so that's mostly the work of this component. Okay, going to the third and the last component that I'll be talking about. So that's the plugins. So for any file system which we want Rubik's to work with, it has to, that engine has to basically implement, we have to implement this plugin corresponding to that engine. And there are two APIs that the engine has to expose. First one is, this plugin has to tell Rubik's how to get the list of nodes which are available in the system, so that Rubik's can, split the nodes, split the file and assign them using the hashing to one of these nodes. And the second one is which file system to use for the remote reads. So for example, you can either be using S3 or Azure file system in the backend. So for that, that has to be specified that has to be told to Rubik's using a separate API. So yeah, for now, I think Rubik contains Presto, Hadoop, and Hadoop plugins, and it works with Presto, Hive, and Spark. And yeah, but to fully leverage Rubik's, we also have to ensure that the splits are assigned to the worker nodes in a certain format, basically the places where they've already been cached, and that is the work that Garvit did. So I think, yeah, he'll continue.
Thank you, Ankit, for the Rubik's context. I'm Garvit. I'm the person who will be speaking about locality-aware scheduling. This is part of my internship project at Cubo. This is part of the work I did then. And so the topics I'll be talking about the Presto scheduler, which is an important component of the planning phase of queries in Presto. I'll be describing how it works, the benefits of having the default Presto scheduler, as well as the reasons why we decided to implement locality awareness. I'll briefly give an overview of the implementation of the locality-aware scheduler in Presto and the expected improvements that it should bring. I'll start by talking about scheduling in Presto. So like it was mentioned in some of the earlier talks, the scheduler is that component of Presto that is responsible for assigning data to nodes in a cluster. It's a very important component. It's part of the execution of almost every single query. In fact, it's responsible for defining the degree of parallelism that query execution can attain in Presto. The default Presto scheduler works by iterating over all the splits that are coming to it, and it finds out which are the nodes which are the least burdened, and it assigns those splits to the least burdened nodes. Here I'd like to talk about certain concepts of scheduling if you're not familiar with the Presto scheduler. So basically splits are units of data. They have a fixed maximum size that is configurable, and the assignment of splits doesn't happen all at once. Splits occur in batches. So that's how the scheduler works. It gets splits, it looks at the splits and sees which nodes are less burdened, and it assigns those nodes to particular splits. Now it seems like a good idea. In most cases, it works very well. In an ideal case, if all nodes are processing data equally fast, it leads to a uniform division of workload for all nodes. But that may not happen very often practically. Some nodes might be processing data faster, some might be slower, some might be lagging behind. In those cases, the Presto scheduler is sort of intelligent enough to know that which nodes should be given more splits to process so that they meet the end goal of having a uniform query execution time. Now you can see that I have started the first statement, uniform division of workload. This is because here we asked ourselves a question: does a uniform division of workload mean uniform execution time for each of the nodes? In most cases, yes. If the data is present in the cloud, for example, and is fetched from the object store, in a uniform division of workload should roughly mean a uniform query execution time. But if the data is present locally in a cache or in the HDFS within a cluster, then that might not be the case. This is the concept of data locality. And if data is present locally, then it is cheaper from an I/O perspective to fetch it directly from the disk than to fetch it from the disk of another node. So we wanted to see whether this can have any impact on query performance, network traffic, other metrics. That's because the Presto scheduler did not consider locality while assigning splits. It only considered how burdened each of the nodes were. It's not the case that Presto does not have any options for locality awareness. Presto has a configuration called force local scheduling that forces the scheduler to assign splits to nodes where they reside. But this has a dependence on the underlying distribution of data within the nodes. There's also something called a topology-aware node selector, which can be configured in a way to give some preference to locality. But we found out that it follows a reservation-based logic, and that may not always work well. It depends on the ordering of splits, upon which we cannot have any control, and the underlying distribution again. So we decided that we need something that can have locality awareness in Presto. And so we figured out that we should follow a simple principle that if locality is a factor, then data should be processed as close to where it resides. We tried out different implementations, carried out different tests, and collected metrics around them. And we decided on an implementation that gives us the best results. So we finalized a multi-stage implementation that tries to do a best effort job to assign splits based on locality while ensuring that there is no skewed distribution of data that is given to nodes for processing. We wanted to adapt the existing property that Presto Scheduler has and ensure that there is no skewness in the query execution time for each of the nodes. I'll be giving a brief overview of the implementation at this point. So the scheduler that we implemented, it has 3 stages. Stage 1 is assignment based purely on locality. If we find out that there are splits which are present locally, they should be assigned to those nodes for processing. Stage 2 is for those splits which were unassigned after stage 1. It is assignment based on compute. This is what the Presto scheduler used to do. Allocate splits to nodes which are the least burdened. They are the nodes which have the maximum slots available. And finally, we have an additional stage, stage 3, which is the stage for redistribution. If we figure out that after assignment has been done in stage 1 and stage 2, for a current batch of splits, if the distribution for processing is not uniform, then we redistribute splits to make it uniform. In this implementation, we have tried to combine multiple aspects of the different scheduling options that Presto provides and try to bring out the best of all of them and gives us consistently good results. That's the objective. Another statement I would like to talk about here is that, so earlier we only used to iterate over the splits once. Here we are adding additional 2 stages. So what does that bring to the scheduler complexity and whether that has an impact on query performance? So we measured the runtimes of the scheduler and we figured out that it's in the order of a couple of milliseconds. And in any case, scheduling for a batch of splits can happen in parallel with the execution of the previous batches of splits. So having additional stages causes negligible impact on query performance in general. That is an observation we made. This diagram here probably illustrates better how the scheduler works now, the locality-aware scheduler. So let's say we start with 3 nodes and have 12 splits. We have a configuration here called max splits per node, which tells us that a node cannot be assigned more than these many splits at once. Here we have 12 splits, out of which 9 are local to node 1. The 10th one is local to node 2, and split number 11 and 12 are local to node 3. This distribution is just for an illustration purpose, and practically we haven't seen a distribution so skewed. But anyway, so stage 1 is assignment based totally on locality. Here we can see that node 1 is given 6 splits, which were local to it. Node 2 is given 1. Node 3 gets 2. And 3 splits remain unassigned. Stage 2 is the one that Presto follows in currently, and that is for the assignment of the 3 splits that were remaining after stage 1. So 7 and 8 go to node 2 and 9 goes to node 3 because they were the ones that were less burdened. After stage 1 and stage 2, we see that there is a disparity in the splits that are assigned to each of the nodes. So that's why we go through a redistribution phase, and we transfer split 5 and 6 to node 2 and 3 so that we maintain a uniform distribution. Now, the redistribution is at some cost of locality, but we are doing this so that each batch has roughly the same distribution. We try to do this in a sort of a greedy manner. We consider that this is the best we can do for each batch of splits. So this is how locality-aware scheduler is implemented. To measure the impact of this scheduler in cases where locality is a factor, we carried out several experiments for different configurations, different size of clusters. And the benefits that we observed that we saw a massive increase in the number of local cache reads. They increased by up to 9x. This reduces some load on the network. We observed that the network traffic reduced as well. And finally, it's because it's cheaper to directly read from the disk than to read from another node's disk or cache. It also resulted in some query performance. I would like to illustrate the observations that we got from one of our experiments. So here we used 3 different clusters. We executed 17 TP-CDS queries on these clusters. We had 10 nodes in each of the clusters. The instance types were i3-4x large. And the cluster that is represented by the green bar, that was plain Presto, nothing attached. The orange bar was the one which had Rubik's attached to Presto, a caching layer attached to Presto. And the blue one was Presto with locality-aware scheduling, as well as Rubik's configured. So when Rubik's is attached to Presto, the data locality factor comes into play. As you can see, this is the plot for query execution times. Having locality awareness in Presto with Rubik's helped us improve the execution times by an average of around 25% and up to 40%. Okay, the file format here was Parquet, and scale was 1000. And however, the more impactful metric that we observed was local cache reads, which sees an improvement of up to 9x when locality awareness is added to Presto. So this is the reason why we went to so much trouble. And yes. We originally designed locality awareness for Presto on Qbol. However, after the community displayed some interest, we were able to push it to Presto SQL as well. It's part of release 3.15 and is available in open source now. The scheduler complexity I already talked about, so yeah, I'm open to questions. Thank you.